Okay, I'm going to try to go over each of these as fast as I can. These are all transformations. You never want to start fresh. You want to start with two or three key points that you know exist on a log 6. And if you can't remember what exists on a log 6, you can do 6 exponent and then just reverse the points. So for instance, when x is 0, y is 6 to the 0, 1. When x is 1, 6 to the 1 is 6. And when x is 2, 6 to the 2 is 36. Now you just reverse these points. 1 comma 0, 6 comma 1, and 36 comma 2. You now have 3 points to work with. Okay? The 3 points to work with, as you may or may not remember, a growth curve looks like this, and a log curve looks like this. Log curves can go on forever for y, so it's YER. X is limited right here at the y-axis, so x must be bigger than 0. As your translation goes to the right or left, this one goes to the right by 1. That means this whole graph now has to go to the right of 1, so x is bigger than 1. Be aware, if there's a minus somewhere, it's going to flip. Practice on Desmos to figure it out. This is a base 5. Let's look at the transformations. All this is a y transformation because it's outside the bracket, so you subtract 5 from all y values. This is an x transformations lie, so you add 1 to all x values. That's it. You take your 3 points, you do that, you find your asymptote, or whatever you want to call it, and you draw it through those points. This one is a base 5. 5 to the 1 is 5, so 1 comma 5 would be on the exponential, or 5 comma 1 is on the log. Logs are inverses of exponential. The only transformation is 1x and 1y. It's going up by 3, and it's going to the right by 1. So now my domain is x is bigger than 1. So notice that the domain is usually x is bigger than this number. And if there's a minus sign in front of this bracket or inside this bracket, it would be x is smaller than that number, the reverse of that number. So I would add 1 to all my x values. I add 3 to all my y values. I create my asymptote at x is equal to 1. Then I draw it going through those points. This is a log 6. The x values I'm adding 3, and the y values I'm subtracting 5. That means the whole thing is here over at x is equal to 3 and looks like this now. It's gone down by 5, so it'll actually look like this. And that means I would add 3 to all my x values and add 5 to all my y values. So those are all pretty straightforward. I'm going to just keep going. So this is to the left, this is to the left, and this is to the left and up 1. This is to the right by 2 and add 1. This is, here's the first one where you've got to, finally, that is not a correct transformation. You have to factor out the 3 inside the bracket. So really we have brackets 3. X plus 11 over 3. That means this whole thing is moving to the left by 11 over 3, not 11. So I would have to multiply all my x values by 3. Oh, sorry, x is lie. I would divide, that's actually going to be a third. I would multiply by everything by a third, or divide by 3, not multiply. And then shift, and then subtract 11 over 3 from all my values. And I would plot my main points. And the y transformation is down 5. This is also not transformed correctly. You'd have to factor out that 2, and you get x plus 1. That means I divide all my x values by 2, and then I subtract 1. You must always multiply or divide first before you apply this. And that's the correct transformation. That's it for that one. So let's move on to the next one. These are the same thing. This might even be the same graph. Oh, no, it's not. Okay, so 3. Oh, yeah, it is the same graph. It just continues on. And then the number key. So this one we have to factor out a 3. Fortunately, there's no minuses here, which make our life easy. Plus 14 over 3. That means I have to divide all my x values by 3 and then subtract 14 over 3. This is the same problem. To factor out 4, I get x minus 11 over 4. So I have to divide all my x values by 4 and then add 11 over 4. There you go, and there's the answer key, so we'll skip that. We'll go on to the next one. So graphing is quite easy, and you should get 100% on that. So always just use your Desmos to practice the nature of these graphs. These have finite solutions, and let's look at what a log is, okay? We've gone over this last time, but this is simply asking, the log is base 5. So this is simply asking what exponent, in this case y, do I put over 5 to get 25? It's clear, 2. So the answer here is 2. Yes, I can do a log base 25 on my calculator. How I would do that is I would do log of 25 and divide it by log of 5 and let my calculator figure it out. But these ones are supposed to be done in your head. It's quite clear because you can figure it out. So this is they're all asking the same question. Here's a base of 3. Y is the exponent. 1 is the result. So what do I put over 3, in this case a y, to get 1? It's clear, 0. So it's over and over again. Now, some of them are tricky. This one you might go, there's no exponent I can put over 16 to get 4. But that's not true. The square root of 16 is 4. And we express square roots as fractions like this. This is a square root. Any fraction, the bottom is the root. The top is the power. So that means 16 to the power of 1 square rooted is going to be equal to 4. In this case, this half is the y, the missing y. All logs ask the question, what exponent here do I put over this base to get this result? So anyway, tricky one. Here's another tricky one. You might say, no, that doesn't work either. But however, this is the other thing you have to learn about exponents. This is a base 2. What exponent do I put over 2 to get an eighth? The question, it is minus 3. Because a minus 3 is really 1, really says take this 2 in the numerator, send it to the denominator, and make its exponent positive. 2 to the power 3 is 8, so 1 over 8. That means the answer y is minus 3. 2 to the minus 3 will get 1/8. If you aren't sure, you can always use your calculator. This is 5 to the 0 will get you 1. 5 to the 0 will get you 1. A tricky one. This one, oh no, that's not tricky at all. The answer is 3. 2 times 2 times 2. This one looks tricky, but the answer is -1. 7 to the -1 is the same as 1 over 7 to the 1. Negative exponents simply mean if it's in the numerator, put it in the denominator, make the exponent positive. You can have negatives in the denominator too, though. 1 over 7 to the -1 is the same as 7 to the 1. So 1 over 7 to the -1 is the same as 7. Okay. 3, how do I get 9? 1/9, -2. They're changing it now. They're saying, we don't, this is actually easier. And it's saying y to the 5 is equal to 32. What is y? Almost automatically, when you see an exponent that big and a number this small, it's almost automatically 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. -half. What is 9 to the -half? Okay, well, do each separately. The negative says I'm going to put it to the denominator with the same exponent. So 9 to the -half simply says, since this is 9 on the numerator, simply says I'm going to turn it into a fraction now. I'm going to put 9 in the denominator, and I'm going to make its exponent positive, a half. A half is a way of saying a square root. So it's 1 over 3. So the answer here is 9 to the -1/2 makes 1 over 3. So y is 1 over 3. 4 to the what makes 1/8? -2. Oh, that's incorrect. This is very tricky. This is making you use your mind a little bit more. So this is asking, what exponent do I put over 4 to get 1/8? 1/8. So what do I put over score to get 1/8? Well, let's convert 4 to a 2. Because what do 4 and 8 have in common? 2. 8 can be expressed as 2 to the power of 3, right? And 4 can be expressed as 2 to the power of 2. But put them both in brackets. And the question is, what do I put as a power here to get 1 over 2 to the 3? Well, I have to get it to the denominator, so I know it's going to be negative. And I have to turn it into 3. The only way I can turn 4 into 3 is to multiply it by 3 and then divide it by 2. When I do that, 2 times negative, so let's figure what that is. 2 times -3 is -6, divided by 2. And it would become -3 if I did that, and that would bring it down here. So that means this is the exponent I need to multiply this 2 by to get it to a 3 down here. Negative to get it down. 3 to turn this into a 6, and then divide by. How did I figure that out? Well, the only way I can make 2 equal 3 is to multiply it by 3, multiply it by the number I want, and divide it by the number it is. So this is an interesting math thing. How do I turn 7 into 122? I take 7 and I multiply by 122 and I divide it by 7, always. So essentially I'm getting rid of the 7 and I'm creating 22. This is also used in sine curves. It's a good way of changing the period of your sine curve. A sine curve's period is always 360. If I want to turn that into 10 seconds, I have to multiply by 10 seconds divided by 360. So anytime you want to turn a number into a new number, you multiply it by the new number and divide it by the old number. So how do the last one, how do I get 9 to 81? That's quite easy, minus 2. So for some reason, this was the only super crazy tricky one. All right, let's go on. Evaluate. Evaluate usually means, well, if they say without a calculator. So they're going to say, well, these are just the tricky ones. And sometimes it helps when they're letters to just use a number. They're saying, what exponent do I put over 3 to get 1? 0. What exponent do I put over 4 to get 4? 1. What exponent do I put over 7 to get 7 to the power 3? Clearly 3. This is a tricky one. This making a log and exponent cancels out this, and it's just whatever's there. 3. To prove it, you can use 10. What's 10 to the log 10? And then just use a number that you know, like 100. We know the answer here is 2. So there's the number I'm looking for. We know the answer log 10 of 100 is 2. So that becomes 2. What's 10 squared? 100. I get the number back. So whenever you have a log base over the base, they cancel out, and it's whatever number is here. What number do I put over 25 to get 5 to the 3? Well, 25 can be rewritten. This is how you analyze this. What number do I have to put over 25 to get 5 to the power 3? Ugh. Well, you have to put 25 in terms of 5. 25 is 5 to the square. How do I turn this 2 into a 3? I multiply it by 3 and divide it by 2. So that means I have to have this as an exponent to turn 5 over 2 into 5 over 3. So what's the answer here? 3 over 2. Okay, you could get confused here because you said, oh, the rule over here is when the base matches the exponent. And here it doesn't. But you can rewrite 16 as 4 squared. So that's a rewrite of 16, so I'll put it in brackets. Log 4 of 8. So over here it's asking what's the log 4 of 8. Well, the rule is exponent times an exponent, so I just move this 2 over here outside. It's now multiplying this. And I'm allowed to put it as a square. Now I can see this log 4 is over this 4, so they cancel. So the answer is 8 squared, or if you want, 64. The answer is 64. If ever you want to do this and figure it out for sure, figure out log base 4, 8. So it'd be log 8. You always start with log 8 divided by log 4. Save that in your memory, put 16 to this power, and you'll get 64. So let's try that out. What's log 8 divided by log 4? I get that. Save it in my calculator. I'm going to put 16 to that power. 16 to the power of my memory. And I'll get 64. Okay, so I did an error somewhere, so I'm going to try this again. Log 8. I know what I did. I didn't hit the equals button. Log 4 equals 1.5. There you go. That's more like it. So I don't even need that in my memory. I can just remember that it's 1.5. So 16 to the power of 1.5 will be 64. And you might even rationalize that this way. 16, what's 1.5? It's 3 over 2. So 16 to the power of 3, and then square root it. But that's how you do it. The first way I did it was the right way to do it. Write the expressions in terms of log, in terms of x, y, and z. So it's essentially figured out in terms of logs. That's interesting. Oh, I see. They want you to break it down the way the other one was combining it. Okay. So what are they asking? You have to reverse the rules. The rules here say, I got to get rid of it. There we go. The rules here say I can rewrite this. Those are two things multiplying. I can rewrite it as log x squared plus log y. Okay, you're just following all the rules. This one can be rewritten in three separate ways. Remember, anything divided is a subtraction. So the first thing I can just say is this is equal to, if I get the wrong equal sign, just ignore me. Log x cubed y squared minus log z. But then I can break this one down into two additions of log y squared. So it's just following the laws of logs. Remember that a square root is simply an exponent of a half. So when I see x square root of x to the power 3, when I see x square root to the power 3, that square root can be expressed as this, x to the half. So put it in brackets, power 3. The rule of exponents is I multiply it. This is 3 over 1. So 3, 2, it's really x to the 3 over 2. Now I can rewrite this in terms of logs. It would be log x to the, oh, that's cubed, isn't it? Yeah, 3 over 2. And by the way, this one would be 2 over 2, which is 1, because the square root of y squared is simply y. So I can just rewrite that as y. So it'll be log x 3 over 2 plus log of y minus log z to the power 4. This is log of x plus log of y plus log of z. This is log of x minus log of y plus log of z. And that would have to be in brackets, by the way. So let's explain that one. This comes out as this. Log of x minus log of yz. But this here, if I'm going to break it down, I have to put it in brackets because it's all together. So that means it breaks down into this. Log x minus log, open brackets, log y, plus log z, because those two are multiplying. Now I can apply the negative to both of those things. So that's the trick there. This one here, the rule of the exponent is this square can be applied to x squared and to y squared. So it's log of x squared minus log of y squared. The rule here is this third can be applied to both of these things. So it's log of x to the third plus log of y to the third. The rule here is this is a square of a half. So it's log of x plus log of z to the half. The rule here is this is 3 times a half, so it's 3 over 2, and this is 3 over 2 as well. So it's log of x 3 over 2 minus log yz, which becomes minus log y 3 over 2 minus z 3 over 2, because this square root applies to both of them. Anytime you have square root of 9 times 81, for instance, you can break that down into square root of 9 times square root of 81. You're allowed to break down things that are multiplied in a square root into two separate square roots. This quarter applies to everything. So it's 3 quarters, 2 quarters, 2 quarters becomes a half, and 4 quarters becomes 1. So this here, Z4 4 root is just Z. This here is just Y to the 2 over 4 half. So that just becomes square root of Y. And this is 4 over 3. So it breaks down, that just becomes, this all just becomes an exercise of specifics. So you're allowed to rewrite that square 4 root as a quarter. That's what a 4 root is. And since x to the third to the quarter, we multiply the roots, just becomes x to the 3/4. Y is a square. When I apply a quarter to it, it's 2 over 4, which just becomes a half, which is just a square root. And then z to the 4 to the quarter, because this 4 root applies to all of them individually, to a quarter becomes 4 over 4, which is just 1, or z. So you end up with this. Log of x to the quarter, to the 3/4 the power of 3/4, plus log of square root of y, or y to the power of a half, minus log of z. Ooh, look at this next one. It's so annoying. Well, you can break it down into two separate things. The first x is multiplying the second x. So let's just break that apart right away and just say, okay, well, it's log x plus log of this mess. Okay? So let's focus on the mess. It's a square root of a square root. What's a square root of a square root? Well, first of all, that square root, this can be rewritten as log square root of square root x, right, as the top, over this square root only applies once to z, square root of z. Well, a square root of a square root is simply an x to a half to the power of a half, because it's a square root of a square root, which is a quarter. So this whole top mess just becomes x to the quarter. And this whole bottom thing just becomes z to the half, which means it just becomes log of x to the quarter minus log of x to the half. Or if you want, 4 root and square root. Okay, moving on. These are just, brain teasers. Just apply this half to the top and to the bottom. 8 to the half becomes 8 z to the power 4. So the bottom is going to become z to the power 4. The y is just going to become y, because y squared, square rooted, is just y. And only the x is going to keep the square root. So it's going to be z to the 4, y, and square root of x. And there you go for that one. Write the following equalities in exponential form. So again, it helps to understand what logs are actually measuring. Logs are simply rewriting an exponent version. They're simply rewriting an exponent. By the way, there's an order to these. These should have been done first before the transformations, but anyway, because these are the easy ones. Rewrite it. This is saying simply 3 to the power 4 is equal to 81. So in exponential form, it's 3 to the power 4 is equal to 81. 7 to the power of 1 is equal to 7. So rewriting an exponential form is like this. This is what they want. A half to the power of 3 is an eighth. So they want a half to the power of 3 is equal to 8. So you just got to rewrite this to the power of this is equal to that. This to the power of this is equal to that. This to the power of this is equal to that. Write the following inequalities in logarithm form. So it's the reverse of what we just did. The reverse says this is going to be the result and this is going to be the base. So the first one is simply log base 8. I don't know how to do it without. Log base 8 of 64 is equal to 2. So it's what exponent do I put over 8 to get the result of 64? 2. The next one is log base 10, or just log, of 10,000 is equal to 3. So what do I put over the power of 10 to get 10,000? 3. The next one is log. So the result is always going to go in the brackets here. The right side is always going to go brackets. The base in this case is 4. And the answer is minus 2. What do I put over 4 as an exponent to get 1 over 16th? Minus 2. They're all like that. So log base 3 of 1 over 81. What do I put over 3 to get 1 over 81? Minus 4. Sometimes the logs are hard to see, but the result isn't. So log base 32. What do I put over a half to get 32? The answer is minus 5. Half to the negative 5 makes 32. How is that possible? Okay. A half to the exponent of negative 5 is the same as 1 to the negative 5, which is just 1. 2 to the negative 5. Well, 2 to the negative 5 at the denominator means I put it at the top, the numerator, with the same exponent, but positive now. 2 to the power 5 is 32. So that means log base half for 32 is equal to negative 5. And then it gets a little tiny bit complicated, but it's the same thing. You just got to find the base over and over again. The result's always on the right. So this is asking, what do I put over x to get y? So what do I do with log base x to get y? The answer in this case is 2 to the power 7. The next one is x to the half, right? So what do I get? What do I have to put over y or over x to get this y? Apparently, it's that square root half. A little bit complicated when they're letters. It's just really an exercise of rewriting it the same way over and over again. And we'd miss the true and false. Next one. We started doing that one. We couldn't figure out what the growth. Oh, there's the new growth rate. 2% after that. So the first year, weird that the thing goes back. The population of currently at 23,000 increase exponentially growth rate per year. When will we have a population of 30,000? Okay. So the growth of this town, based on time, starts at a population of 23,000. We're going to multiply it 1 plus whatever percent it is. 2% is represented as 2 over 100. Since 1 is the same as 100 over 100, what's 100 over 100 plus 2 over 100? It's 102 over 100. So that's what I multiply it by. And it's every year, so it's to the exponent of y. The question is, when will this left side be equal to 30,000? So you take the 1 over 2 divided by 100 to the exponent of y. You divide both sides by 23,000. On the right side, these zeros all cancel. And I get 30 over 23 is equal to 1 over 100. 30 over 23 is equal to 1 over 100. To the power of y. The only way to solve this is take a log of both sides. So you get log of 30 over 23. And you can take lns too, doesn't really matter. Of log of 1 over 2 over 100 to the power of y. Now the rule is I can put y over here. Now to solve for y, divide both sides. This is just a number. You can always find out in your calculator that's just a number. 1 over 102 divided by 100 is simply this number. 1.02, that's an increase of 2%. Take a log. That's the number. You can always put the number on your math sheet, but you're going to lose out on the accuracy. So that means what I'm doing to solve this is I have to take this first one, divide it by this one, and that's what y is. So what year will it occur? Well, it's when it's log 30 over 23 divided by log 1 over 2. So I'm going to clear my memory just in case it's all clear. So 30 divided by 23 is the first one. You take a log, and that's divided by log, open brackets. My thing is you do the number first. That's it. 13.47. If you're worried about getting it wrong, 30 over 23. You can always do the second one first, 102 divided by 100. I'm going to clear it. 102 divided by 100, which I know is 1.02. You could have just put 1.02. Now I can take a log of it. And then I can put it in my memory. Then I can comfortably take the log of the first one. Got to hit equals first. Take a log of that. And divide it by my second one, my memory. And I should get my years again. 13.417 was the number of years. So it'll take 13.417 years before this town grows to a population of 30,000. And if your teacher wanted it by months, there are 12 months in the year. So 0.413 times 12 gives you roughly the third month. And then the 0.013 could translate into days. So 0.013 times 30 days. And you'd figure that out as roughly a third of a day. So third month, the first day, third way through the day. The population of purple martins in Algonquin Park is estimated this in 1992. 10 years later, it's risen. So this is the final age. This is the initial age. We know it's a growth rate, so this number in here is going to be bigger than 1. And it's the power, how many years passed? 1992 to 2002 is 10 years. So it's to the power of 10. So there's some mysterious number that's bigger than 1. I'm going to just do this. Focus on this question. There's some mysterious number here. We're going to call it x. That's to the power of 10. And then multiplied by the initial population, that's going to be equal this growth. So first step is before, it's the same thing. We divide both sides by this number to get rid of it. We can simplify the zeros. So we get 444 over 350. How do you get rid of a power of 10? You 10 root it. 10 root it. This is on your calculator is this. You put the number in, you press this symbol, and then you put the root that you want. So that means I have to find the 10 root of 444 over 350 to figure out what my x value is. So let's do that. 444 divided by 350 first. And now I got to go to second function, x to the y to the power of 10. 1.02, so this is the number that x is. How do I express this in a percentage? Because I want annual growth rate. Well, that's the same as plus 1 plus what? Oh, 0.0240. Let's just round it up to this. So what if I were to express this as a percentage, I would have to multiply it by 100 to get the percentage. 2.48%. So the growth rate is 2.48% because the town is growing by 1 plus this is the growth. Estimate the population for 2010 to the nearest 100. Well, now we have our formula. Our formula is the final population is equal to the initial population times 1. Well, we can use the exact number we got to the power of whatever my years are. 2010 from 1992 is 18 years. My initial population here was 35,000. So I'm going to take 1.02, whatever my fraction is, to the power of 17, because exponent's first, and multiply it by 35,000. Fortunately, I have the exponent still in there, so I'm going to put it in my memory. Oh, I could have just didn't even have to do that. I could just do second power, or first power, x to the y. I want to put it to 17. Hit equals, then multiply it by my population. If you get a population that's smaller than the first one mentioned, 44,000, you did something wrong because the first one grew 10 years, and this is more than 10 years, so the population should be bigger. And sure enough, my population is 5244.918, whatever. And again, there should be some rounding, but your teacher's not doing it. So it's probably 52445 is the population after this amount of time. Constructing these is very useful because when you grow older and want to do your own finances, these are the ways you do it. For instance, if I have 2,000 saved, if I have 2,000 I want to put in the bank now, and I want it to be 10,000 in 10 years, it would be this. What growth rate do I have to find to do this? I divide both sides by 2,000. 10,000 divided by 2,000 is 5. So and then I take a log 5. Oh, actually, I don't have to do that. I take a 10 root. So what's the 10 root of 5? It's going to be equal to x. So if I want to turn 10,000 into 2,000 in, well, I can't remember what I did, 10 years? Yeah, 10 years. If I want to turn 2,000 into 10,000 in 10 years, I need to find this 10 root rate 1.1746. What rate is that? Well, that's 100%, 1 plus 0.17. That's 1 plus 17.46%. It's almost impossible to find something that'll grow that fast other than business and real estate. Certainly not the stock market, maybe crypto, but you might go the other way. So that means I can't do it. Not realistically. I'd have to find, but this is important because then I can say, oh, I have to save more than 2,000 this year to have 10,000 in 10 years. if I know a stock, for instance, that will pay off 8%, I can do the calculation and figure out how much I have to save. So for instance, if I want to save 10,000, but I don't know how much I have to save, but I know I can get a rate of 10%. Well, 10% is the same as 1.1. It's very hard to find 10%, by the way. And then I know I have 10 years. Okay. So now it's just a simple matter of what's a 1.1 to the power of 10. It's this. So that means I can replace this. And let's just call this question mark X. So what's 2.5? I have to divide both sides by 2.159. So 10,000 divided by 2.59. I'm going to just cheat and do it. 2.59 divided by 10,000. Hit equals and then flip it. So that means I have to save, if I can find an investment that pays 10%, I have to invest $3,855 today and leave it alone. $3,855 today and leave it alone for 10 years. Very useful actually in life. One of the very useful things in life, because we actually have to do finances our entire life. There's a growth rate. That's something that goes up. This is a financial growth rate. And the I is the rate of interest and the T is the time. This is a decay, half-life. You have a half. And notice that's the thing we figured out. You have to put time over whatever the half-life is to get the correct exponent. And that's the initial amount. This is a doubling. Anything that doubles is 2. Depends on how much time it takes to double. So it's T divided whatever time. So if I tell you it takes 10 days, we're working in days then, it's T over 10 will be my exponent. And that makes sense because in 10 days, when I put 10 in for time, 10 divided by 10 is 1. I will effectively double. This is a pH log, so you always take the negative log of the concentration of hydronium. This is the decibel, intensity of sound. This is an earthquake. No, yeah, earthquake. So it's the magnitude, where M is the magnitude, I is the intensity. I don't know what S is. But anyway, that's earthquakes or logs. So here we can see the question's half-life, so I have to use the half formula. Population increasing, I have to use this one. Population, has it risen? Yes, it's risen, so I have to use this one. Yeah, we just kind of did that. Accident nuclear plant. Oh, that's not good. This is like Chernobyl. 5 hours later, this is the level 2. So now we know that every 5 hours we get a reading, but that's not half. But we can get an idea. But we have to use a radiation. So let's say, did they tell me? So I have to reach that to be safe. So we only know what's happened in 5 hours. So this is an interesting one. I think the other ones you can do on your own. This is an interesting one. We know that the initial reading was 800. We know it's being multiplied by something that's less than 1 because it's decaying. And we know that after 5 hours, it reached, so let's call this less than 1x. It reached 800. Sorry, the initial was 950, not 800. So went from this to 950. So we know 950 times x to the power of 5 for 5 hours, it reached 800. Well, our first step is dividing both sides by 950. Our next step is 5 root. The 5 root of this will tell me my decay rate. It will be less than 1. So 800 divided by 950. 5 root. So this is my decay rate. X is equal to. What does that mean? Well, if we look at it in terms of 1 minus what is equal to this number? Well, we just have to add x to both sides, or if we want, we can just subtract 1 from both sides and then divide by -1. So we're going to subtract 1 from both sides. and then change the sign. This is my decay rate. That means it's decaying by 3.37% each time. 3.37%. So I can either write my decay rate as 0.96 like that. I could write it as, yeah, actually, we're just going to take it like that. So now we know that this is the decay rate. Final radiation is equal to initial radiation times the decay rate to the power of time in hours, because we start with hours. The 5 doesn't matter because they didn't tell us every 5 hours it decays. Well, we don't know the final radiation, but we do know we want to reach a final radiation lower than that. So we'll just use that. Anything after that will give me that. My initial radiation was 950. So I'm going to start by dividing both sides by 950. Then I'm going to take a log of both sides, because I'm trying to solve, whenever you got to solve an exponent, mysterious missing exponent, you have to use log. Now I can bring that t down in front, so it's t times this, which means I can divide that on both sides to get rid of this, which means the time it will take to become safe is going to be this. So I'm going to keep, now I have that nice exponent in there. I'm going to add 1 again. I'm going to make it negative and add 1. I already have that nice decay rate in there, so I'm just going to save it to memory. Clear it. I'm going to take the log of 0.01, but I have to divide it by 950 first and hit equals before I click my log. So that's my log up top, and I'm going to divide it by the log of my memory. And I get this many hours. Remember, we were working in hours. So the time it takes to be safe is over this many hours. Now, technically, we don't talk in 333 hours. So I have to take this. And how many hours can I fit in there? Well, 5 times 60 is 300. So we're talking about 5 hours and 33. Oh, sorry. That's 333 hours. So we want to talk in terms of days. How many 24s can I fit in this number? So we're talking 13 days and whatever's left. 13 days times 24 is equal to 10 times. So it's the same as 10 times 24, which is 240, plus 3 times 24, which is 72. So we're talking 72. So 5 days is 312. 312 hours is 5 days. So if I subtract the 312 from that 333, I'm left with 21.4 hours. So it takes 5 days and 21.4 hours to become safe. It takes over that to become safe. This one I think we started with, so it's just the rules of log. This is a product, 8 times 3, so this is log of 84. This is just a multiplication. X times x plus 2 becomes x squared plus 2x, so it's simply the log base 2 of x squared plus 2x. We did all this. The 2 becomes exponent, becomes a, yeah, we did all these ones already. It's just following the rules of logs. Solve them. So when you hear solve, it means you have to actually come up with a number. Interesting. Ln. What is ln? Ln is simply the log with the base of e. So e. That should be e. E is a magical number, 2.81. It's equal to minus 3. So how do we solve it? Well, e to the power of negative 3, we rewrite it in terms of exponents. It's going to be x. So x, whatever's here is always the result we're trying to get. This is always the exponent on the right. and this is the base. So I just take my calculator, and I take the symbol E, 2.718, sorry, and I put it to the power of -3. And I get this. So solve x is equal to that. If I want to prove it, just take this number and press ln, and I should get -3. Ln is ln on your calculator. There you go, get -3. Ln is simply the log base e. Okay, how do we solve this? Well, we have to look at it in terms of subtract. Actually, I should go in order. Okay. Oh my goodness, what is this saying? Well, log is a base 10. So it's saying 10 squared is going to be equal to this. It's going to say 10 squared is going to be equal to 3x minus 2. 10 squared is 100. I add 2 to both sides. And I divide by 3. So x is 102 divided by 3, whatever that is. To prove it, just do the log of 102 divided by 3, and you should get 2. Oh, okay, I made a little, well, good thing I did it, because I made a little error somewhere. So it's saying 10 to the squared is equal to 3x 2. It's equal to that, 3x. So 102 divided by 3. If I take the log of, well, I did something. So that's this. It's simply asking. 10 squared is equal to 3x. What is x? Oh, I see. I solved for x, and then I took the whole thing. Yeah, x is equal to 1 over 2 divided by 3. So I have to put it right in there. When I multiply that 3 times this, the 3's cancel. 102 minus 3 is minus 2 is 100. So of course log of 100 is 2. The next one is number 3. So go in order. So this one looks annoying, and it is. And the secret here is this is actually quadratic. You just can't see it. First thing you should do is say, oh, well, that 2 can actually be expressed as a square. If I get it all to the same side, and log 2 here is just a number. If I get it all to the same side, I got log of x squared. We can always write it like this, log of x squared minus, because I'm bringing it to the other side, log of 3x minus 4 minus log of 2 is equal to 0. Now I just let x equal log of x, and then replace everything where I see log of x with an x squared. Oh yes, so let's, so we have to sort of, before we do that, I have to rejig this in order to come up with, this has to look like log x somehow. So let's see, actually, let's see if I can do it a different way. These are all base. So I'm getting log x squared minus log 2 minus log 3x minus 4, yeah, is equal to 0. Well, the rule of log is saying I can take log x squared, and when I subtract this one, it's log of x squared over 2. Okay, let's try that. So I can rewrite this first one as log of x squared over 2. And and again, the best thing I can do is, these are the same base, so now I can just take 2 times that. There we go. All that over nothing. So let's leave the left alone, sorry. And this is the same as log of 2 times 3x minus 4. 2 times that is 6x minus 8. Great. This is going to be squared over here. So squared, like that. So far, so good. When I subtract it, when I get it to the same side, this becomes, so I'm going to subtract log 6x minus 8 from both sides. It's going to be equal to 0. This can be rewritten like this, a log being subtracted. It's the same as this. Is equal to 0. But log is base 10, isn't it? Log, this whole log here of this thing, which is x squared divided by 6x minus 8, is base 10, which means 10 to the 0 is equal to this mess. 10 to the 0 is equal to this mess. So I can get rid of log. I can rewrite this as 10 to the 0 is equal to this mess. Well, 10 to the 0 is 1. Now I have x squared divided by 6x minus 8 is equal to 1. So I multiply both sides by this denominator. I get this. X squared is equal to 6x minus 8. Now it becomes a quadratic. I subtract 6x from this side. So I get x squared minus 6x plus 8 is equal to 0. Now the thing I'm looking for is factoring. Get rid of that. Is factoring. I want a number that multiplies out to 8 and adds up to minus 6. I don't think it's possible. Oh, no, it is. Minus 2 and minus 4. Now, before you say this isn't possible answers because they're both negative, wait. So the factors of this are this. It's equal to 0, which means x can be 2 or x can be 4 is my possible answer. But before you conclude that, take these numbers and put it into this one over here. What's 3 times 2? 6 minus 2, log 2. So that's fine. What's 3 times 4? 12 minus 4, 8. So that's fine. It works here too. And this one works. So it works in both cases. So what does that mean? Okay, so I'll put them on the right to show you what that means. It means 2 times the log of 2 will be equal to the log of 2 plus the log of, when x is 2, 3x, 3 times 2, minus 4. That's 6 minus 4, which is 2. So, of course, 2 times log 2, what's 2 times log 2? It's simply log 2 plus log 2 is equal to log 2 plus log 2. Now let's see if it works for 4. 2 times log 4 is going to be equal to log 2 plus log of 3 times 4, 12, minus 4, 8. 8. So the question is, does that work? Well, to do that, we can do it like this. We can say log 2 plus log 8. Is that going to be equal to, let's see if I can do it in a way that makes sense. Log base 10 is tough to see it. Well, I could put it in my calculator, but also this is this. Becomes log of 16. So does log 16 equal log 2 plus log 8? Let's see. Does the log of 16, 1.204, equal the log 2 plus log 8? It does. So that works as well. So that means the answer is 2 or 4. That one was sort of tough. What about this one? Same sort of thing that we just did. Solve the sort of left as much as you can first. We can't really do anything because they're adding. We can't really do anything on the left because they're adding. Let's see, what's the secret here? Log x is equal to that. Well, this is a tough one. I might have to come back to it. 4 times x can be rewritten. I believe that can be rewritten in the front. Ooh, let me pause. Yeah, of course, I'm just tired. So whenever you see them added like this, it means we can multiply them. So this is the same as x times x minus 1, which is x squared minus x, is equal to log of 4x. Well, I can subtract log 4x from both sides. 0. And now we've got this. Log of this thing here is the same as x squared minus x over 4x. is equal to 0. It's the same thing we just did, actually. This is saying 10 here. So we can rewrite that as, we can get rid of the log and say 10 to the 0 is equal to this mess on the right. Well, 10 to the 0 is just 1. You can multiply both sides by 4x. You get that. And it becomes a quadratic again. It becomes x squared minus 4x. Oh, there we go. X squared minus x minus 4x becomes minus 5x. Essentially plus 0 is equal to 0. Or just this, x squared is equal to 0. When does this happen? Well, we can take x out of both and get x minus 5. This happens when x is 0 or when x is 5. Sorry about that minus. So there you go. Now you would plug it back in. 0 does not work because right here this becomes a negative. 0 minus 1. So 0 is not an answer. Log 5 plus log 4 will be equal to log 20. Log 5 plus log 4. So here's log 5. Here's log 4 plus log 5. So that's 1.3. Now we should be equal to log 20. 1.3. So the answer is x is equal to 5. Plug it in here to confirm. Same one. It was the same thing as the last one. This is equaling a number, but it's the same thing. This can be equal to this. Is equal to 3. So it's just essentially saying, since this is base 3, it's saying 3 to the power of 3 is equal to this mess. 3 to the power of 3 is 9. 3 to the power of 3 is 27, sorry. Multiply both sides by this denominator. 27x minus 27. So you get x plus 25 is equal to 27x minus 27. You put your x's, you subtract, you leave the 25 over here and you add 27. And you leave the 27x and you subtract x. So you get 26x is equal to 52. Divide both by 26, get x is equal to 2. So if you go back to the original calculation, which is here, and you put 2 for x, you get this. Log base 3 of 27 plus log minus log base 3, it's 2 minus 1 of 1, is equal to 3. Well, log base 3 of 27, 3 cubed is 27, so the answer here is 3. Log base 3 of 1, how do you get 1? By 0 is equal to 3. 3 minus 0 is indeed equal to 3. I think they're all like that. Yeah, these you multiply. These you multiply. These you multiply. Okay. Well, I think that's all I can do for now. Okay, prove the following statements. Proving things is actually quite hard. Proving is actually quite hard. So how can I prove this is true? How can I prove this is equal to that? Okay. Might take some time, but let's try a technique. They're not the same base, right? But square root of a half, or square root, is the same as base to the half. Okay. This here is the same as x squared. There is a rule in here, and I'm just trying to figure it out. Oh, I know what I can do here. This is saying that this base to this power will be equal to that, and I have to prove it. So this is the result there. You can also reverse it. I can say this base, and this might make more sense, this base to this power should be equal to that. My big problem is I forget how I can transfer a base of a half. So I'm going to use a base of a half to this power should be equal to x. Should be equal to x. I think I see it. So now I can take this 2, and I should have left it here. So what's the rule of power of power? This half can multiply that power. Half times the 2 becomes just 1. The rule for any base to the power of its log means it cancels. That's just a rule. So x is equal to x. I think they're all going to be like that. So be aware that 1 over square root of b is the same as 1 over b to the half, and that this is the same as b to the negative half. So b to the negative half simply means put the b to the half in the denominator, and b to the half is the same as square root. So what they're saying here is that base over here is the same as this. This base here is the same as b to the negative half. So they're saying b to the negative half to this exponent is going to be equal to this result. It's going to be equal to this result. Well, the rule of exponents is I multiply them. So this negative 1 times a half becomes positive a half. I can rearrange this. Oh, it becomes positive a half. Yeah, it becomes positive a half. I can rearrange this as an exponent here. And then I can see this log b here cancels out with this log b. So x to the half does indeed equal x square root. And then this one, it's the same thing over and over again. They're saying here that b to the 4 to this power is equal to x squared. Well, the rule of exponents is b to the 4. I'm allowed to put this here, but then I can also put this 4, sorry, not quite a 4, up here. I can see this b to the b cancels out. So is x squared to the 4, is x squared to the 4 the same as x? Is square root of x to the 4 the same as x squared? Well, square root of x is x to the half to the 4. 4 times a half becomes 4 over 2. 4 over 2 becomes 2. So indeed, x squared is equal to x squared. Given that this is equal to x, and this is equal to y, and this is equal to z, express the following expressions in terms of this. Okay. Each time I have to do it over and over again? Oh my God. All right. Well, I'll try. Log 12 is the same as, I have to look at what I'm working with. Log 2, log 3, log 7. Okay, it's 3 times 2 times 2, isn't it? I can break down 12 as 3 times 2 times 2. 3 times 2 times 2 is 6, isn't it? There's 12, rather. Right? Okay. That means I can rewrite this as this. God, I hate that. Log 3 plus log 2 plus log 2. And I've been told that log 2 is the same as x. And that so that means I can replace log 2 with x. And that log 3 is y. So that means log 12, in this case, it's the same as y plus x, which is y plus 2x. Annoying, stupid. So log 200 is the same as log of 2 times 100, which is the same as, I got to figure out ways of expressing this into 2's. Geez, 2 to the exponent of 2 times, no. This is a tougher one. 3 times 7 is 21. 7 times 2 is 14. Let me pause and think this one out. This one's tough. Oh, I got this pretty tricky, actually. This is the same as 2 times 100. 100 can be expressed as 10 squared. Oh, hang on. I got to do it a little bit better than that. Let's see if I can do it a bit better than that. But yeah, I got to pause and do it again, sorry. Yeah, I think I've got to use division here. So I've got to come up with ways. 200 is the same as, like for example, 400 divided by 2. Right? So I've got to figure out ways of creating a number up top that has multiples of 7 and 3. So I might skip that one for now and move on to this one because this one's easier. 14 up top can be expressed as 7 times 2. And 3 below is fine. So really we're talking about log of 7 times 2. 7 times 2 minus log of 3. 7 times 2 can be expressed as log 7 plus log 2 minus log 3, which means we're talking about z plus x minus y. So z plus x minus y. So that's easier. 0.3 is the same as 10 divided, or 3 divided by 10. It's got to be an easier way, so I'll come back to that. 1.5 is 3 divided by 2. There we go. So this one is 3 divided by 2, which is the same as log 3 minus log 2, which is the same as y minus x. So some of them are tricky that I'm not really seeing right away. Log 15 is the same as 5 times 3. Okay, that's fair enough. Oh boy, some of them are not easy. Oh, 15 is definitely something divided by 3. It's 45 divided by 3. Yeah. Yeah. We can do 79, 7 times. I haven't used 79, 21. So I got to figure out uses of 3, 7, whatever that come to these numbers. So some of them are obvious, some of them are not. So 0.3 is 30 divided by 10. I can see what's going on here. 10 is an easy number to get rid of. There we go. So going back, so those easy ones, fine. Okay, log of 200 is the same as log is 2 times 100, which is the same as log of 2 plus log of 100. Well, log of 100 is simply the number 2. Log of 2 is, we're told, is x. So that's what they want, x plus 2. Log of 0.3 is simply log of 30 divided by 10. And the top is simply log of 3 times 10. I'm not allowed to break it up like that. Am I allowed to break it up? Like that. There we go. Which simply becomes log of 3 plus log of 10 minus log of 10. This is simply 1, 1, 1, which is log of 3, and we've been told that log of 3 is the same as y. In other words, 10 to the negative 1 is, so here, we can just take log of 0.3 as an answer. Yeah, okay. So we're just going to rewrite, just to be clear. How did we get 0.3? 0.3 is the same as 3 divided by 10. There we go. That's 0.3. So log of 3 divided by 10 is the same as log of 3 minus log of 10. Log of 10 is simply 1. Log of 3, we've been told, is x. So is y. So y minus 1 is the equivalent of this. So that's why it stumbled me. 15 here is the same as 3 times 5. But let's do it in tens. 1.5, yeah, we got 1.5 here is what I'm trying to get at. 1.5. How do we get 1.5 from 3? 3 times 5, yeah. 10, we're going to use multiples of 10 though. That's a little tougher one because there's still can't see it. 10.5 is interesting. 105 divided by 10. 15 is the same as 5 divided by. So some of these are still interesting. 6 is 6,000, which is 6 is 3 times 2 times 1,000, right? So that's 6,000. That can be represented as log 3 plus log 2 plus log 1,000. Log 1,000 is simply 3. All divided by log 7, so subtract log 7. We've been told log 3 is y, plus log 2 is x, minus log 7, which is minus z, plus 3. This is the expression for that. Kind of all stupid. It's going to take me a bit more time to figure out what this is. So it's 5 times 3. Okay, fair enough. That's the same as log 3 times 5, which is the same as log 3 plus log 5, which is just a number. So I guess I can just leave it like that. And log 3, I've been told, is y. This is 3 times 0.5. So that becomes log 3 plus log 0.5. Log 0.5 is just a number. Log 3 is represented by y. So y plus log 0.5. I think that's what they're getting at. Kind of stupid. Kind of don't like it. Okay, let's continue. I'm going to just finish. Solve the following. Then I got to stop. Okay, 3 to the x minus 12 is equal to 2. So let's put it to the... I imagine you're allowed to use logs here. Oh, come on. God, I hate that. So let's add 2 to both sides. We get 3 to the x is equal to 14. We take logs of both sides. So this becomes log x times log 3. Let's see if you can figure out how I got there. So that means x is equal to log 12 divided by log 3. Just, you can actually, if you just leave it like that, that's incredibly accurate. What about this one? You take the log of both sides. When I take the log of both sides, I get this. On the right, I'm allowed to bring down the exponent down. That's the exponent. Times log 3 is equal to log 2. So 1 minus x is equal to log 2 divided by log 3. If I add x to both sides, or if you want subtract, you can divide by 1. So let's just add x to both sides, make my life easier. And then so x is equal to 1 minus log 2 divided by log 3. This is incredibly accurate. You don't have to solve it. 4 to the x, 4 to the power of x, this is an interesting one, is equal to 5 to the power of x plus 1. You've got to take a log of both sides. So you get x times the log of 4 is equal to x plus 1 times the log of 5. I'm going to start by dividing both sides by log of 4. And then you're going to divide both sides by x plus 1. No, you can't do... Oh, you're going to expand that. You're going to expand the left side. Get x is equal to log 5 over 4. 5 over log 4 times x plus log of 5 divided by log 4. So that's the... I'm just going to use the LG here. LG. So that's just a number. How do I got to get x all alone. Now I'll divide by x there. No, I did this one wrong. I think I can subtract. Can I subtract? So that's just a number multiplying x, really. Okay, let's look at it like that. Log 5 over log 4x is equal to log 5 over log 4. And on the left, this is just a number. So if I were to turn these into numbers, for instance, on the left, I would just get this. What's log 5 divided by log 4? It's 1. No, that's not right. Clear my thing. Log 5 divided by log 4. I get this. So you get x minus... Oh, actually, you know what? I can just do it like this. This is smarter than coming with the decimals. On this left side, I can factor out x. I get 1 minus the log 5 minus 4, like that. And this, by the way, should have been log 5 divided by log 4. And now I can divide off this multiplier, and I get log 5 divided by log 4, all divided by that little bracket. 1 minus log 5 over log 4. These are all numbers on the right. That's what x is equal to. Annoying. But that's all you're doing over and over again. You're taking logs of both sides and then solving for x. So when I take logs of both sides, the exponents come down. I get 1 minus x times log of 6 is equal to x times log of 10. That's kind of nice. That's just 1. Log of 10 is just 1. 10 to the power of 1 is equal to 10. So I get that. Yeah, you got to multiply this through. I get log 6 minus x, log 6 of x is equal to x. Now I've got to add that to both sides, plus log 6 of x. Now I can factor out an x on the right side. I get 1 plus log 6. Then I can divide it. So log x is going to be log 6 divided by 1 plus log 6. You can always put it in your calculator to see if that's true. And over and over and over again, some of these are hard to do this. You got to get rid of the fraction. Seeing as I see e, it's smarter to use ln whenever I see e. So I'm going to multiply both sides by this denominator first. 10 is equal to 2 times that. So I get 10, and then I'm going to expand the left side, is equal to 2 plus 2e to the negative x to the power of negative x. I'm going to get rid of that 2 here, so I get 8. And I'm going to divide both sides. No, I can't divide both sides. I'm going to take a log of both sides. Ln, log, ln. Oh yes, I'm going to put this as an exponent. So 2, I can't do that yet because it's not ln. So I'm going to take a ln of both sides instead of a log because I can see x. So ln of 2e to the power of negative x. So that means I can now take the negative x down here. Great. Now I can divide both sides by ln e. So negative x is equal to that. And then I can divide both sides by negative 1. So x is equal to ln 8 divided by ln 2e. Ln 2e, what do I put to the exponent to get 2e? Yeah, that's not just a number, so just leave it like that. So they're all like that. The next one's tricky because I cannot do it the way it is. I have to get the 12 to the other side. I can't do it like that. That's interesting. Something to the power to something to the power. Okay, I've got it. Keep in mind that this is the same as this. Anything to the 2x is the same as 5 to the x squared. Let 5 to the x be x. I get x squared minus x minus 12. I'm looking for a number that multiplies out to minus 12 and adds up to minus 1. So I get x minus 4 and x plus 3. So that means x is either 4 or minus 3. So x is either 4 or minus 3. Now that's what that is, but remember I made x be 5x, so that means 5 to the power of x is equal to 4, or 5 to the power of x is equal to minus 3. Well, there's nothing I can put to the power of 5 that will come out as minus 3. So I can take a log of both sides, log of 5 to the power of x is equal to log 4. I can take that x in front. And then I can divide both sides by log 5. So x is equal to log 4 divided by log 5. So that's how you do these. I got to run for now.